The successful Mars rover landings are among humanity's greatest achievements and most spectacular events. But this is no longer news. But have you ever wondered how they are controlled and operated from here on Earth? From more than 225 million kilometers away and with a signal delay of over 12 minutes. Or what is the command that makes a rover move on Mars? The challenges are immense, and to make it harder, this precise rover control process can't tolerate mistakes. A mistake in choosing the best path for the rover to follow could end up causing the rover to crash into a rock or put it on a steep and dangerous slope, which poses a risk of overturning, for example. A mistake in how close the rover should get to a cliff to make observations, for example, could end up causing the rover to fall off instead of just getting close to observe. And perhaps the most common of them, a mistake in choosing the best path, or at least the one that is less dangerous for the rover, could end up causing the wheels to get stuck in the Martian sand, making it impossible to get it out. That's exactly what happened in 2009 with the Spirit rover. While moving the rover for another drive during Sol 1899, one of the wheels ended up getting stuck in the soft Martian sand. The team desperately tried to free the rover, but unfortunately without success. And to make matters worse, one of the wheels stopped working, leaving the rover with only 4 operational wheels out of the 6 it has. After several months of unsuccessful attempts, the mission was redefined as a stationary platform. In other words, even a tiny mistake can cause 10 years of hard work and a rover worth billions to be completely or partially lost. And one of the key components for the entire communication process with the rover to begin or even be possible is the Deep Space Network. A set of 3 facilities containing antennas spread across 3 different and strategic locations on Earth. One in Goldstone in the United States, another in Madrid in Spain, and the last one in Canberra in Australia. These facilities are located at strategic points in order to create an almost total coverage of the Earth, so that no matter which direction the Earth is facing in relation to Mars, it is always possible to send or receive signals. In each of the 3 facilities, there are several antennas, some of which are 34 meters in diameter, and one giant antenna that is 70 meters in diameter. The enormous surface allows it to pick up extremely weak signals. Another important piece is the satellites that orbit Mars, like the Mars Reconnaissance Orbiter and the Mars Odyssey. With all this equipment set up, and once the rover is on Martian soil, it's possible to start controlling it, so that the signal sent from here on Earth to the rover with requests like take pictures, record a video, move 15 meters forward and turn 90 degrees to the right, or inspect that rock, can reach the rover. It needs to have antennas to receive such signals. In the case of the Perseverance rover, just like Curiosity, 3 antennas. The first and also the most frequently used to transmit data to Earth is the Ultra-High Frequency Antenna, or UHF antenna, which operates in the 400 MHz range. Due to transmission capacity limitations, the data transmitted by this antenna is first sent to the satellites orbiting Mars, and through them, using more powerful antennas, it is later retransmitted to Earth. There's just one problem. For this data to be sent to the satellites orbiting Mars, the rover needs to be in line of sight with the satellite. And that happens once per Martian day, and the window for data transmission is about 8 minutes. After that short window, the line of sight is lost and the data can no longer be transmitted. During that time, between 100 and 250 Mbps of data can be transmitted from the rover. The second antenna on the Perseverance rover, just like on Curiosity, is the X-band high-gain antenna. This is a high-gain antenna, and that's why it's used to both transmit and receive signals directly from Earth without going through the satellites. This antenna moves, which allows it to be directed to always point toward Earth, thus maintaining a constant line of sight with Earth, which will be constantly moving in the skies of Mars. This antenna operates in the 7 to 8 GHz range, and the data transmission or reception rate varies from 160 to 500 bits per second if the 34-meter antennas of the Deep Space Network are used, and from 800 to 3,000 bits per second if the 70-meter antennas are used. The third antenna is the X-band low-gain antenna, primarily used for receiving signals. This antenna can receive but also send signals at low transmission rates in any direction, meaning it is omnidirectional, and because of that, it provides a robust means of communication with Earth through the deep space network, operating in the same 7 to 8 GHz range. Due to the huge delay in the signal sent, the commands related to the operation and movement of the rover are usually transmitted to the rover as a package containing several commands. Instead of just telling the rover to go forward, which is also possible, the command is much more complex and comprehensive. After selecting the destination and analyzing the terrain, the engineering team sends a package of commands for the rover to receive and execute. This set of commands can be something like move forward, 5 meters turn right, 90 degrees, and take a panorama. Before executing these commands, the rover itself also analyzes the surrounding terrain and, depending on the mode, decides whether it is safe to move forward as requested or if it is better to go around. To avoid a possible danger zone, since the rovers are equipped with hazard avoidance software, which is a risk analysis system, basically to control or drive a $2.7 billion rover that's more than 200 million kilometers away, via radio signals and with a delay of about 12 minutes. The team of NASA engineers combined sophisticated software, virtual reality, high-resolution satellite images and data obtained by the rover itself, and 3D glasses. All of this is combined into a sophisticated and highly detailed 3D environment that looks a lot like a game, which allows the engineers to safely control and drive the rover from here on Earth. And the software that generates this 3D environment for the controllers here on Earth is called RSVP, or Rover Sequence and Visualization Program, which has been continuously improved over the years and was initially used for the Spirit rover. There are basically 3 driving modes for the rovers: blind driving, which is the simplest, but also the most dangerous. It basically consists of pointing the rover in a direction and simply making it go forward for a few meters. However, it's risky because it's based only on visibility, and some terrain obstacles can be more dangerous than they seem. The other is visual odometry, which is a technique that basically consists of estimating how much the rover has moved based on how many rotations the wheels have made. However, the rover's wheels tend to slip a lot on uneven surfaces. That's why, to increase accuracy, both Curiosity and Perseverance use only the cameras to take before and after photos, and with that, estimate how much the rover has moved. This is a fully autonomous rover system. And finally, there's the Auto Nav mode, where the team of engineers chooses a target or destination, and the rover tries to reach it completely autonomously, while using its risk analysis systems to avoid dangerous zones detected by its systems, as well as those highlighted by the team. And the efficiency of these software systems was proven right in the first drives of the Spirit rover back in 2004 during Sol 106, when the rover avoided a 21 centimeter rock along the way, as well as some others, completely autonomously. And here you can see this route taken in visual odometry and auto nav mode, replayed in the Rover Sequence and Visualization Program, or RSVP. The cameras that make up the hazard avoidance software are the HazCams, located at the front and rear of the rover. There are 6 HazCams in total, 4 in the front and 2 in the back. So that's basically how a rover on Mars is controlled from here on Earth. Quick reminder, I heavily summarized this process,